This is a new idea that I thought up a while ago, but I haven't really written it down in a VIXA article or made a presentation on it, but I'm going to try to make the best presentation as I can right now. When you look up pictures of solar granulation on Google Images or Bing Images, you'll find that they include, flat pictures of the sun, the little granulations of the little gas bubbles coming up. And if you do see a picture where it has a cross-section of the granule, it has it labeled as hotter gases going up, cooler gases dropping down. So the convection works as the oven. Hotter gases move up, cooler gases go down, and it convects like that in the cells. Now, what I noticed is that if you have an ionized gas, chances are, if it's ionized, it will recombine and release heat. That's a simple phase transition. It's called plasma recombination. It's exothermic, meaning heat releasing. It releases heat, light, microwave energy, radio energy, a whole bunch of different kinds of electromagnetic energy. That's why we can see the sun in many different frequencies. It's because of plasma recombination at the surface. So what happens is the ionized gas, which is particles. Now, I'm going to use generalizations because I'm not too sure if particle theory is correct, but I'll use generalizations of that. So you have your ionized protons and your electrons. They move upwards, and then they combine with each other. And when they combine with each other, the proton combines with the electron, it releases heat as an exothermic reaction. Now, I bet you're wondering, how did this ionized gas get there at the bottom below all the gases being formed? Well, what happens is that you have gas molecules gaining energy as they drop, because the sun's gravitational field is really strong. The escape velocity is over 600,000 meters a second. That is a boogieing, okay? That's faster than your NASCAR. That's really freakishly fast. So the gas falls down at that velocity, and then what happens is it reaches a point to where it reionizes because it reaches its critical ionization velocity. And the highest velocity for a critical ionization velocity, I think, was only 50,000 meters a second, and that's for hydrogen. So this is well above that range. So literally, it can ionize all the gases from gravitational potential alone, from the gases falling into the center. And then once it reaches down here, after it's been reionized, it moves back up again as freely charged particles and is electromagnetically forced back up into the solar granule again. And that's why the sun is really, really freakishly big and wide, is because of that electromagnetic forcing due to the ionized material, the plasma, forcing everything up and out. Meaning you don't need a nuclear burning core in the center to radiate all the heat. The ionized gas forces itself up. It pushes against itself. It expands by great amounts. As well as when you push all that ionized gas up there and it recombines, man, you have so much heat up there and a whole bunch of different kinds of chemical reactions that can take place. Of course, this is a generalization of it. But to overview, you have the velocity gained because of gravitational potential energy, and then you have the critical ionization velocity, meaning you get that particle moving fast enough against the other plasma that's in the vicinity, it will reionize. And even if you pump more energy into it, it'll just ionize more and it will be a sustained plasma. And then it will force itself back up through the center again. Very similar to regular gas convection, where hotter gases expand and then when they cool, they contract to become denser. So not only is density a part of this, but electromagnetic forcing is, and the critical ionization velocity, how fast you have to let that material go to get it ionized. And once it's ionized, it moves back up, recombines, releases energy, and then falls down because it's denser, and it gains energy again from gravitation, and then it comes back up again. So you have these big convecting cells that, you know, you look up on YouTube, granulation time lapse, you'll see these cells convecting like that. And obviously, these walls are where the material moves down and they squeeze like a sandwich. So they're like, literally like cells for biological organisms almost. But there you go. Today is July 9th, 2015. I don't know if I went over that again. Stay there.